Welcome back everyone to EGME-333 Fluid Mechanics. In this video we're going to discuss the mechanical energy equation. With the conservation of mass, most of the time pipe flows can be analyzed with the conservation of energy. Here it is written in its general vector integral form. However, we can simplify this equation using the following assumptions. By assuming that the flow is steady, incompressible, and consists of one-dimensional inlets and outlets, this helps us simplify the components of the left-hand side of the equation. Additionally, we can treat any forms of heat transfer and changes in internal energy as mechanical losses. We can then rearrange the conservation of energy equation and write it as the following, which we often refer to as the mechanical energy equation, where W sub shaft represents the shaft work per unit mass done by either a pump or a fan, and alpha represents the kinetic energy correction factor, which is typically set to 1 for most flows. So what this equation is saying is that the net mechanical energy going into a system plus the work delivered by a pump or a fan must equal the net mechanical energy coming out of the system plus all of the losses. We can apply the mechanical energy equation to a pipe system that consists of a single inlet and a single outlet to further simplify it, where now we have H sub L, which represents the total head loss of the pipe system, where the first part, H sub lowercase l, represents the major loss, which is the head loss due to viscous effects in straight pipes, and the minor loss, H sub m, which represents the head loss in a pipe system due to its various pipe components. Now, I'd like to briefly compare the mechanical energy equation to the famous Bernoulli equation. By looking at the mechanical energy equation, you might notice a striking resemblance to the Bernoulli equation, which is written as the pressure divided by the specific weight gamma plus v squared over 2g plus z, the vertical position. The sum of these three quantities remains constant along a streamline. Now, if we make the following assumptions for the mechanical energy equation, in which we neglect the viscous effects in the pipe system, meaning there are no head losses, and no work is being done on the pipe system, then the mechanical energy equation reduces to the following. So, one could argue that the Bernoulli equation may be interpreted as the conservation of mechanical energy for an inviscid flow. Often, the mechanical energy equation may be referred to as the modified Bernoulli equation. With the mechanical energy equation, we introduce the concept of losses inside a pipe system. So let's dive further into that topic by first considering the steady flow through a horizontal pipe with a constant area. For this case, let's first apply the conservation of mass. For a steady flow with one-dimensional inlets and outlets, typically the mass flow going in must equal the mass flow coming out. If I label my inlet as 0.1 and my outlet as 0.2, then m dot 1 should equal m dot 2. If we expand this out, we have that the density at 0.1 times the mean velocity at 0.1 times the cross-sectional area at 0.1 is equal to the density at 0.2 times the mean velocity at 0.2 times the cross-sectional area at 0.2. Recall that I'm assuming that the flow is incompressible. Therefore, rho 1 must equal rho 2. Also, because the pipe consists of a constant area, a sub 1 equals a sub 2. So these two quantities can be canceled out of the conservation of mass expression. And what we're left with is that the mean velocity at 0.1 must equal the mean velocity at 0.2. So the idea is that in a horizontal straight pipe with a constant area, the mean velocity remains constant. So if we apply the mechanical energy equation to this problem, we can simplify by considering that we know that the mean velocity at point 1 is equal to the mean velocity at point 2. Also, because we are dealing with a horizontal pipe, we know that this flow experiences no vertical displacement. Therefore, Z1 is equal to Z2. Lastly, there is no pump, fan, or turbine within the control volume of interest, so we know that the shaft head is equal to 0. Consequently, the mechanical energy equation reduces to the static pressure at point 1 minus the static pressure at point 2. This difference divided by the specific weight of the fluid is equal to the head loss of the pipe system. What we can then argue is that the total head loss is proportional to the pressure difference between the inlet and the outlet.